All right, we're going to focus on zeros of polynomial functions. In this section, we are also covering the intermediate value theorem and just polynomial applications in general. So here we go. So it says find a polynomial function that has the given zeros x is 0, 2, and 5. And it says hint many correct answers. Actually, there's an infinite amount of answers. There's an infinite amount of polynomial functions that could have these three same zeros. But we just want to come up with one. So I'm going to give you guys a minute to just try this on your own, just especially with what we just talked about in our last section. I want you to think about how could we come up with a polynomial function instead of going the reverse where we're solving for these. So go ahead and put me on pause and let's see what you can do. Okay, so if you weren't exactly sure where to start, we want to start thinking about these guys right here. What we'd like to do is turn these zeros into factors. So for example, if I know that x equals 0 is one of my zeros, then I know that x is a factor. For this one right here, if x equals 2 is a 0, then x minus 2 must be a factor. And last but not least, if x equals 5 is a 0, then x minus 5 is a factor. Okay? So once we turn these into factors, now we just want to multiply them together. As you can see, I've done here. I started by multiplying the binomials together first and then distributing the x last step. So here is my final answer. Remember I said hint many correct answers, and that's because, I could put, let's say, a lead coefficient here of 2. And eventually, once I get to this step, everything would be multiplied by 2. And I could get with any number, right? We could also, we could also throw in another 0 in there. It didn't say it had to be a third degree. It didn't say that these had to be the only three. So many possible solutions. Okay, this next one, it says find a polynomial function that has these three zeros, 4, 2 plus root 7, and 2 minus root 7. Now, this one's going to be a little bit harder, so I'm going to help you guys out with the first step. Okay, so just to get us started on this one, and then I'll have you guys try to finish it out all the way through. So very similar to the last problem, I do want to write these three zeros as factors first. So I did x minus 4, x minus the quantity of 2 plus square root of 7, and x minus the quantity of 2 minus root 7. Now, here's where this gets a little bit hard. I mean, essentially, it's like we're just multiplying this all the way out, but it seems like a disaster. It's just a lot of work to do that. So we're going to try to make our lives a little bit easier. So if you look at my step 1 compared to my step 2, you should notice something different about the location of the parentheses. So I am using the associative property to regroup my set of parentheses here. So now I have x minus 2 plus root 7 and x minus 2 minus root 7. And that's really significant because now when I multiply these together, boom, it's really x minus 2 squared minus root 7 squared. This should remind you of dots, difference of two squares. Okay, so now that I've done the hard part for you, what I'd like you to do is I'd like you to actually multiply this out, combine like terms, multiply the x minus 4, and see what our final polynomial function would be. So go ahead and put me on pause. Okay, so let's check it out here. So once I multiply this out, x minus 2 squared, I get x squared minus 4x plus 4, and then minus 7 from here. I combine like terms, and then I'm going to multiply these two together, which seems like a doozy, and honestly it is. And then my final step to get my answer would be to combine like terms. So this would be my final solution. It has those three zeros that we stated in the directions. Okay, so let's talk about multiplicity. Multiplicity would be how many times a zero occurs. So what does that mean? So it is possible for us to get a 0. So for example, let me write this. If I had the graph, let me get a real line here. Okay, let's say I had this graph, just y equals x squared. Okay, now it would have an x-intercept at 0. X equals 0 would be one of its zeros. But technically, it has a multiplicity of 2. If I'm looking at the degree here, I know that it has 2 total roots. How does that happen? Well, because it has this bounce, which is what I'm going to talk about in even multiplicity here. So let's talk about these. We have odd multiplicity. The graph will pass through the 0 and cross the x-axis. We could also have even multiplicity, such as in this case. Even multiplicity, the graph would touch the 0 and bounce back up, not crossing the x-axis. So even if this had been an x to the 4th function, it would look very similar. It would have a bounce at that root. So for example, just to show us an odd multiplicity, y equals x cubed. That graph looks like this. Okay, at 0, I have my 0, x equals 0 again, but that has a multiplicity of 3, okay? So it says here, find a polynomial with the given zeros and multiplicities and has that degree. So first I have a 0 of 5, which has an odd multiplicity of 3. I have a 0 of 0 with a multiplicity of 2, and my degree should be 5. So if I do this, if I write 5 as a 0, that's x minus 5, and it has a multiplicity of 3, so b to the power of 3. 0 of 0 would just be x, and its multiplicity is 2. And you can just leave your answer like that. There's no need to multiply this all the way out. That would just be mean. Okay, this one, and I'm actually going to have you try this one on your own first. You're going to sketch a graph of a polynomial function that has these conditions. So just a rough sketch. It needs to be a 4th degree. Think about how that affects your end behavior. It needs to have 3 real zeros and a negative lead coefficient, which also affects our end behavior. Let's see if you can come up with an answer here. There's many, 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 many answers. Let's see if you can come up with one. Go ahead. Okay, so beginning this problem, I really want to focus on what the 4th degree and negative lead coefficient will do to my graph. So it really will help us understand our end behavior. So it's 4th degree, negative lead coefficient, so I know that the ends of my graph are going to be down, down, right? Then it also said that we want to have 3 real zeros. So here's one graph I came up with. It has the correct end behavior. It has 3 real zeros, 1, 2, 3, right? It has a bounce here, which gives it that 4th degree. 1 root, 2 roots, just think of that's a double multiplicity, and 3 roots, or sorry, that's the 4th root. So 1, 2, 3, 4. Another idea, just a slightly different one, is this. So end behavior satisfies the conditions. So that's 1, 2, 3, 4. But technically, I did only have 3 real zeros.